All right, so now that we're done with limits of sequences, we'd like to move on to talking about limits of function. And I realized that we had not talked about complex functions yet, so here's a quick definition. So let's say we're given some subset of the complex plane S, then a mapping f from S to C is called a complex value function if for every z in S, the map f assigns a unique complex number to that point there. Right? So every value in S is sent over to some unique value in C. So what we can't have happening is a point Z cannot be sent to multiple points. All right, so in that case, we call f a complex valued function. So given a complex valued function f, what we can do is we can write f as in terms of real valued functions u and v. Right? So what that means is given a complex function f, which takes a complex number to a complex number, we can write it as in terms of real valued functions u and v, where u and v are going to take a complex number in S into some real numbers. And how does that work? Well, u of z is going to be the real part of f of z, and v of z is going to be the imaginary part of f of z. Right? So just like we did with sequences, we can take a function and we can split it up into the real part and the imaginary part, which means we're going to have two real valued functions. All right, so now that we have the definition of complex valued function and this notion of splitting it up into real valued functions, what we can now do is talk about limits of function. All right, so we say limit as z approaches a of f of z is equal to L if for every epsilon greater than 0, so now we can pick any epsilon. If we pick this epsilon, we're going to find a delta bigger than 0 such that whenever z minus a is less than delta, f of z minus L is going to be less than epsilon. All right, so let me repeat that. For every epsilon greater than 0, we can find a delta greater than 0 such that whenever we pick any z that is in a open disk of radius delta centered at A, we know that f of z is going to be in an open disk centered at L with radius epsilon. All right, so we're gonna come back to this definition here in a second, just again intuitively tell you what this is saying. But again, we can relate the limits of complex valued functions to limits of real valued function in the following way. We say the limit exists if and only if both the imaginary part of f and the real part of f, the limits exist. All right, so limit z approaches a of f of z exists if and only if limit as z approaches a of the real part and limit as z approaches a of the imaginary part exist. So now we're going to get a real valued function. Admittedly, this real valued function is going to have two variables, right? So it's going to be in terms of x and y. But we have reduced this question of computing the limit of a complex function to computing the limit of two real valued functions of two variables. Right? So there's a slight trade-off there, but again, it's nothing too terrible. All right, so let's again go back to this definition here. So what this says is, so let's say we fix an epsilon. And then for every epsilon, we can find a delta such that the following happens. So what that means is, let's say I have here's my A, and so here's my L. So what this means here is for every epsilon greater than 0, so we're going to fix an epsilon. What we can do is we can find a delta that's bigger than 0. So if I fix an epsilon, I'm going to get a delta such that if I look at everything in this open disk here, so I have an open disk centered at A of radius delta, everything in this disk here is mapped by F into this disk here. All right, so I'm going to fix an epsilon. I can find a delta, so that if I take anything in this disk here, it's going to get mapped over to this disk. So F sends this disk here to that one there. That's what it means for the limit over there. All right, so again, as I change epsilon, this delta is going to change as well. But the point is, no matter what epsilon I pick, I can always find this delta here. So that's what it means for limit as z approaches a of f of z to equal L. So now that we are familiar with the definition here, we are going to look at the following example. All right, so I should briefly mention, in this course here, complex analysis, we are not going to be doing as much analysis as you would do in real analysis. So even though this entire course can be done very carefully like we would do real analysis, if we do that, then we don't get to see the bigger picture. So the compromise we're making is we're going to do less of the analytic part and see more of the ideas. All right, so in this particular example here, so what I want to do is I want to look at this function here, which is given by z over the conjugate of z, and I want to show that this limit as z approaches 0 does not exist. All right, so first let's write z as equal to x plus iy. And so, and this is something you've seen in Calc 3, but the same thing applies. So for complex limits to exist, limits from all directions must agree. So all limits from all directions must agree. Right, so starting, what does that mean? So let's take z of bar. I can write this as x plus iy divided by x minus iy. I can do that, right? So first, let's approach 0 along the real axis. So along the real axis. All right, so along the real axis means we're going to fix y is equal to 0. So in this case here, the limit as z approaches 0 can be written as x0 approaches to 0, 0. And in this case, I get x plus 0 over x minus 0. Right, everyone hopefully is following. So what I said is we need to find the limit as z approaches 0. Remember, z approaches 0 means x plus iy approaches 0 plus I0. So we can do that along any direction. So what we're going to do is we're going to come fix the y is equal to 0. So I'm going to approach this point here along that direction, see what happens. All right, so when I did that, I got that the limit is equal to 1. And now, second, what we're going to do is we're going to approach along the imaginary axis. So if I'm approaching along the imaginary axis, if I'm on the imaginary axis, we are fixing that x is equal to 0. So in this case here, I get limit as 0y goes to 0, 0. And in this case here, I get 0 plus iy. In this case, I get 0 minus iy. So when x is equal to 0, that's what I get. And everything's going to cancel out, leaving me with negative 1. So do these limits agree here? No, right? So since limits don't agree, the limit does not exist. Oh my god, I can't even make a smiley face. There we go.